All right, so we're going to start with chapter 3. We're going to start with chapter 3. Okay, the first section in chapter 3 just reminds you of a few things. So for example, I'm just going to highlight a few things from them. Remember, E is located in your calculator. E is a irrational number that goes on forever, but E is just a number. It's a symbol in your calculator. It's used in formulas, but it really is just a number. Because that number goes forever, it's a naturally occurring number, that we just call it E. It's a button already programmed in your calculator. Now, when we talked about interest, you don't have to memorize these, but there are different formulas for different things. So if you're doing simple interest, this is the formula you would use. If you're doing compound interest, this is the formula you would use. If you're doing continuously compounding interest, this is the formula you would use. Now, why am I showing you these formulas? And you're probably saying, we've done these formulas before. We kind of plugged them in. We practiced the calculator. We talked about them a little bit. Well, this is to tell you how much is in your account. So if you plug into the first one, simple interest, it will tell you how much is in your account. Same thing for the other two. What if I want to know how your account is changing? Then I have to take the derivative of this. Then you have to know how to take the derivative of an E, how to take the derivative of something raised to a number, how to take the derivative of maybe things that are being multiplied. So these are common formulas that we use to find how much money is in your account based on simple, compound, or continuous interest. But what if I wanted to take the derivative of them? Not basic derivatives anymore. We're going to have to learn a little bit more. So just introduce those formulas. Again, especially the one with the E. How do you take a derivative of an E? How are we going to figure that out? Okay. Then there's some examples. I'm not going to do it. I'm not going to do it because we've done these examples before where we plug into the formula. We've seen those formulas before. There's some problems that you can kind of try. You may see a problem like this in your homework. So that's why I want to point it out, is if you're trying to find doubling time or tripling time, there is a formula for that. That if you want to find out doubling time, it's the ln of 2 for doubling, divided by the rate. If you want to find out when will it triple, that's the ln of 3 divided by the rate equals the time. And if you want to find out when it quadruples, you do the ln of 4 quadrupling divided by the rate, and that gives you the time. These are just problems that could come up. That's the formula to do it. Okay. But again, you'll notice I'm going a little faster through these because we're going to apply these. This is just the introduction to these. And we've already seen these. We've seen all these formulas when we covered chapter 1. Okay. Now, section 3.2 is where we're going to spend our time. And what we're going to spend our time is on special case derivatives. Special case derivatives. And when I say special case derivatives, these are the weird ones. These are going to stick out. These are going to be different. And once I go over them, you'll know what I mean. So there are going to be in total 4 special cases. Okay. Now I'm going to a whole separate document and I'm going to ask you to go to your separate sheets. Here's where we can make a nice notes sheet for our special case derivatives. And later on, we're going to add product rule, quotient rule, chain rule, elasticity, some other stuff. So let's label this special case derivatives. And there's going to be 4 of them. Special case derivatives. Now, when I say special case derivatives, what I mean, these are the weird, these are the special, these are the interesting ones. Okay. Now, I'm going to be honest with you. The way the book does it is they show you a little bit and then they wait 2 or 3 more sections and they show you the full. The reason why they do that is the reason why you need to learn a little bit more. I prefer just to show you it all. And then when we get to that point, I'll just remind you how we got there. So the first special case is e to the x. Now, again, when I say special, this one definitely is special. E to the x, that doesn't show up very often. That's a unique one. That's a special case. And you're going to like this one. The derivative of e to the x is, drum roll please, e to the x. That's it. Doesn't change at all. E to the x. Now, again, this is where they would stop and move on. I'm going to take it a little further because some of you may be saying, what if it doesn't look exactly like e to the x? What if it was e to the maybe 7x? What would happen? What if it was e to the 7x? What would happen? What would be going on there? Well, it would still be the same thing. Okay, how do you take the derivative of e to the 7x? Step 1, rewrite it. E to the 7x. And then you're like, I don't feel like I'm done. And you're right, you're not done. What happens is you didn't deal with the 7x. So step 2, what's the derivative of 7x? 7. So your final answer, I would write 7e to the 7x. 7e to the 7x. And again, you're probably saying, well, why didn't you do that for the first one? Technically, I did. Because what's the derivative of 1x? 1. And if you multiply by 1, does it change anything? No. That's why I don't like showing just this one and moving on. Because what if it was a little more complicated? So if you're the person that likes steps, here are the steps. Step 1, rewrite it. Step 2, derivative of the exponent. Okay, let me do one more and I'll see if we have questions, and we still have to practice this. But this is for your notes. So what if I had 8e to the 2x squared plus 5? Well, when you take the derivative, if you have a number in front, and that's going to be consistent through all the special cases and the ones we do, the number in front stays in front. The number in front stays in front. Step 2, the derivative of e to the 2x squared plus 5, you rewrite it. E to the 2x squared plus 5. But as you're doing that, you feel, I don't think we're done. And you're right. The reason why we're not done is we haven't dealt with the exponent. Then we take the derivative of the exponent. What's the derivative of 2x squared plus 5? 4x. Good. The derivative of 2x squared is 4x. The derivative of 5 is 0. You have just completed the derivative. Okay? So to talk about that, talk through that. The 8 stays in front. Number in front stays in front. The reason why is product rule, which we'll learn a little later. Then, how do you take a derivative of an e? Step 1, rewrite it. Step 2, derivative of the exponent. And then, kind of what you learned last test, maybe it's not the derivative that's the problem. Maybe it's the simplifying that's the problem. And to simplify, 8 times 4x is 32x e to the 2x squared plus 5. So this would be your final answer. So we're going to pause here, see if we have any questions, and then we need to practice. But this sheet you're going to keep beside you. Anytime you see an E, you can look at your sheet and figure out what to do. So remember, all 4 special cases are going to be special, weird. This one's weird because e to the x. So have that sheet beside you. Now I'm going to give you some examples to try. Okay? So let me give you a little random sample of problems. Okay, give those 4 a try. Give those 4 a try. You're going to find the derivative of all 4. Okay? You have your notes that you can refer to. Please feel free to add to them. Some people like to have steps. Some people just like the example. Those notes are for you. Okay, so we're going to work on these one at a time. The derivative of e to the x would just be e to the x. But again, if you want to know why, the process is not just e to the x is e to the x. It's step 1, rewrite it. Derivative of the exponent would be 1. E to the x times 1 is just e to the x. So again, you can just go straight to e to the x, but that's the y. That's the y. Okay? Now, again, start figuring out the process. To take the derivative of e to the negative x, step 1, rewrite it. Step 2, derivative of negative 1x is negative 1. Therefore, you get the answer. I would write it as negative e to the negative x. Now, if you want to put negative 1, that's fine. However you want to do it. But again, the process is the same for all of them, right? Rewrite it, derivative of the exponent. Special cases. Okay, now what happens if there's a number in front? Well, if we're taking a derivative, the number in front stays in front. The reason why is product rule. We'll go over the product rule a little later. Okay, then how do you take a derivative of an e? Step 1, rewrite it. Step 2, derivative of the exponent, which is 3. And then where a lot of people are going to make mistakes, probably not in this one, but maybe when it gets harder, the simplifying. Negative 2 times 3 is negative 6e to the 3x. Okay, careful, careful, careful. And then the last one, I put a fraction in there. Hopefully that doesn't make anything too much harder. It shouldn't. The 1/3 stays in front. E, this is rewrite it, e to the 1/2 x to the 4. And then derivative of that. The derivative of 1/2 x to the 4 would be 2x to the 3rd. So again, if we're making a mistake with the derivatives or making some sort of mistake, that's what happens. And if it was me rewriting it, I would do 1/3 times 3, which is 2/3 x to the 3rd, e to the 1/2 x to the 4. And that would be your final answer. So again, kind of what you're learning is that once you understand how to do it, it's the details. It's the details. It's the details. Okay, let me give you one more and then we'll move on. Okay, let's say we had, let's go with 1/2 e, and let's just make the top really long, x squared minus 4x plus 2. Okay, give that one a try. So when I take the derivative, what's going to happen? Again, if you need to write the steps, write the steps. The 1/2 stays in front. How do you take a derivative of an e? Rewrite it. E to the x squared minus 4x plus 2. And then the last step, derivative of the exponent, which would be 2x minus 4. Notice I'm not teaching you how to take the derivative of little things anymore. We've moved on and we're building on. Okay? Now, could you leave this as your final answer? You could. But we could also simplify it. So what I mean by that is I can distribute that 1/2. And if you distributed the 1/2, you would get x minus 2 e to the x squared minus 4x plus 2. And if that is your answer, is that correct? No. It has to be in parentheses. Now, some of you are saying you're just being picky. Hold on. The difference between this one is whatever x minus 2 is, multiply it by that. If you take away the parentheses, now it means something different. It means x minus 2 times that. It's a totally different statement, right? So the parentheses do matter. The parentheses do matter. That would be your. So the first special case is e to the x. The second special case is ln of x. Again, these are the ones that stick out. These are the ones that are different. These are the ones that are interesting, right? So let's add to our notes the second special case. Again, the way your textbook does it is it introduces it slowly, which is just the first box. The first box is if you have the ln of x, if you did it the long way and repeat it over and over again, you would find the pattern that it becomes 1 over x. So what is the derivative of ln of x? It's 1 over x. What's the derivative of ln of x? Natural log of x? It's 1 over x. But if I stopped there, you're not really getting the complete story. Yes, that is true. The derivative of e to the x is e to the x. The derivative of ln of x is 1 over x, but that's not the full story. So I'm going to add to it, which will come later in the chapter, but it's a good place to put it now. What if it wasn't just ln of x? What if it was ln of x squared minus 4x plus 2? What if it was a little bit longer? Then what would you do? Well, then you're going to learn how to really take the derivative of ln. It's still the same, but it's just longer. So here's how you really do it. Now I'm going to emphasize, some of you like words. Put words, step 1, step 2, step 3. Some of you like examples, great. But are you going to remember your own notes tomorrow? That's what you got to think about now, okay? So how do you take the derivative of an ln? Here's really how you do it. It's 1 over the original inside, x squared minus 4x plus 2. It's 1 over whatever you're taking the ln of. That's that 1 over x stuff. But if you do that, there's something inside of you that's saying, I don't think we're done. And you're right, because I never dealt with the inside. So step 2 is the derivative of the inside. And the derivative of the inside is 2x minus 4. So your final answer will be 2x minus 4 over x squared minus 4x plus 2. Now, another way that some people explain the derivative of ln, which is a good way as well, is how do you take the derivative of an ln? The derivative is on top, the original is on the bottom. If you prefer to do it that way, no problems at all. The derivative of the inside is on the top, the original is on the bottom. I like to break it up just to show you the steps. 1 over the original times the derivative of the inside, but it ends up being the same. Okay? So we're going to do one more for the notes, and then we'll do some examples to practice. So one more for the notes. What if we had 10 ln of 4x cubed minus 5x squared? Okay? So to take the derivative nice and slowly, it's all about how to do each part. The number in front stays in front. The number in front stays in front. Times 1 over the original, 4x cubed minus 5x squared. So just pause there a second. The number in front stays in front. 1 over the original times the derivative of whatever is inside there, and that would be 12x squared minus 10x. I know I squeezed that in there, but I'll rewrite a little bit nicer below. So on top, we have 10 times 1, which is 10, times that 12x squared minus 10x over 4x to the third minus 5x squared. And again, this is the simplifying part. If I wanted to simplify this a little bit more, I would distribute the 10 and have 120x squared minus 100x over 4x to the third minus 5x squared. Now, you could simplify it a little bit more by factoring out an x, but let's just leave it like that for now because we don't want to lose the main idea. The main idea is how to take the derivative of an ln. Number in front stays in front. 1 over the original times the derivative of whatever you're taking the ln of. And then, believe it or not, what's going to be the hard part later is simplifying. Simplifying. So we're going to do a couple examples, but we're going to step it up just a little bit. We're going to step it up just a little bit. Instead of giving you, 4 little ones, I'm going to give you 2 longer ones. So here's the first one. I want you to take the derivative of ln of x minus 4 ln of x plus 2/3 ln of x squared minus 5. Oh, x to the 4. Let's do x to the 4. Okay, and then here's the second one. Second one is going to be e to the 4e to the x minus 3e to the 5x squared minus 3x minus 2/3 ln of x plus 1/2 ln 0.2x to the third minus 7x. And you're like, that's it? That's it. And again, just go nice and slowly, see how much we can do. So we're going to go ahead and take the derivative of the first one. And we're going to go nice and slowly. First of all, this is the original. When I'm showing it's the derivative, we always put the little prime, little derivative. And the first one, the derivative ln of x is just 1 over x. Okay, it's 1 over x times 1, which is just 1 over x. For the second one, the 4 stays in front. And then the derivative of ln of x is 1 over x. We'll simplify that in a minute, but it's 4 times 1 over x. Then the third one, the 2/3 stays in front. And then I have ln of x to the 4th minus 5. So that's going to be 1 over x to the 4th minus 5 times the derivative of that, which would be 4x to the 3rd. Because the derivative of -5 is 0. So let's first make sure that we got that correct. Then make sure you simplify correctly. Simplify. When we simplify, again, it's not to make your life harder, it's to make it look easier at the end. So the first one is 1 over x. And instead of doing minus 4 times 1 over x, that's just 4 over x. It looks a little bit nicer, it's a little bit cleaner, all that. Then here, what could we do? Well, there's a couple things. If you want to look at this as a numerator, this is 2 times 1, which is 2, times 4, which is 8. So the top is 8. The bottom, we have 3 in parentheses, x to the 4 minus 5. And then again, if this one you want to distribute, this would be 3x to the 4 minus 15. Okay, so the idea is we're cleaning it up. Now, oh, don't forget the x. Okay, now if you want to put 8/3, that's fine. There's a lot of different ways of writing this. But what I would probably do is leave it as this. I would leave it as 1 over x minus 4 over x plus 8x over 3x to the 4 minus 15. That's probably how I would leave it. But again, there are so many other ways or total ways that are also correct. I don't want to go too far down that road. We found a correction. Remember, this is 4x to the 3rd. Thank you for catching that. So that would be 3rd. That would be 3rd. Thank you for catching that. Observation that you can simplify a little bit further because we have 1 over x minus 4 over x. That's minus 3 over x plus 8x cubed over 3x to the 4 minus 15. And again, not to get too lost in the simplifying, but the more simplified, the better. The more simplified, the better, but they're all correct answers. It's just the most simplified would be the easiest to use at the end. Okay, so I'm gonna give you a little bit more time on the second one, and I'll probably give you a little bit more space. So we've covered 2 out of 4, so we're going to start mixing already. So when I do the derivative, now we have our sheet on the side in case we need it. But how do we take the derivative of 4e to the x? The 4 stays in front. The derivative of e to the x is e to the x. That's the first one. Second one, the minus 3 stays in front. Now we have e more than just x, which the derivative is 1. So we're going to have to, step 1, rewrite it. Step 2, derivative of the exponent, which would be 10x minus 3. Again, if we're not sure where that came from, we need to know how to take our derivatives, right? Everything is building, everything is building. Then the next one, the minus 2/3 stays, and the derivative of ln of x is 1 over x. Then the last one, 1/2 stays. Now we have ln of more than just x, so we're going to go through our process. 1 over the original, 0.2 x to the third minus 7x times the derivative of that, which would be 0.6 x squared minus 7. And we'll pause there before we simplify it. Now, as we do the second part, which is simplifying, what's interesting, you're like, oh, how am I going to simplify this thing? You're more worried about the algebra than the actual calculus, right? So it always goes back to the algebra. So be careful. Don't be afraid of it. We just have to be good at algebra. So the first one's good to go, 4e to the x. The second one, if I wanted to simplify, now again, you could leave it the way it is, but if I wanted to simplify it, I can distribute this 3 in parentheses, and that would be 30x minus 9 times e to the 5x squared minus 3x. Again, you could also just leave it the way it is. You could also distribute the negative 3 and make it positive. There's a lot of other ways to do that, but you would simplify, try to clean it up a little. The next one, this could be written as 2 times 1 is 2 over 3x. Okay. And then the last one, again, if we're like, oh, how am I going to clean this up? Well, 1 times that leaves you with 0.6 x squared minus 7. On the bottom, we're going to distribute the 2. So that gives you 0.4 x to the third minus 14x. So I would probably leave it like that. But again, if your concern is the algebra simplifying, don't lose the point. I'm not teaching algebra simplifying. I'm teaching special case derivatives, right? But you may be worried about the algebra, but don't lose focus on the special case derivatives. First special case, e to the x. Second special case, ln of x. And remember, ln is natural log, natural log. So maybe you can guess what the next one's going to be. We're going to take the derivative of log. We're going to take the derivative of log. Okay, so let's go back to our special case sheet. And let's add the third one. The third one is going to be the derivative of log, the derivative of log. So again, it starts basic, then we'll do a little more involved. So the first one is going to be log base 2 of x. Now, if I compare natural log to log, besides ln and log, a big difference between natural log and log is logs have bases. Logs have bases, but essentially they're both logs. The only difference is, how do I deal with the base? And the answer is this. Well, actually, I'll keep them side by side. So how do you take the derivative of a log? How do you take the derivative of a log? It's going to be 1 over whatever you're taking the log of, which in this case is x. And you're like, that's the same thing, except for how do we deal with the base? And to deal with the base in the denominator, ln of the base, ln of the base, ln of the base. So basically, natural log and log are very similar because they're both logs. The difference is, how do you deal with the base? And the answer is, in the denominator, you put ln of the base, ln of the base. Now, your next natural question is, what if it wasn't just log? Pick a number, any number. 5, that's funny, that's what I was going to use. 5, and then let's say it was something longer, like x squared minus 2x plus 1. Well, how would we take the derivative of that? And the answer is 1 over whatever you're taking the log of, which is, in parentheses, x squared minus 2x plus 1. But in the denominator, to take care of the base 5, we put ln of 5. Then, just like natural log, we're not done yet. The next step is derivative of whatever you're taking the log of. And that is 2x minus 2. So your final answer is 2x minus 2 over, in parentheses, x squared minus 2x plus 1 times ln of 5. So if you look at natural log, it's the derivative on the top times the original on the bottom. Log is the same thing. Derivative on the top, original on the bottom. The only difference is How do we deal with the base? We put ln of the base on the bottom. We put ln of base on the bottom. Okay, so let's do a couple log examples. I'll give you example number 1. F of x equals 7 log base 5. Well, let's do, we already did 5. Let's do, pick another number. 7 and 7, keep it the same. 7 log of x. And then the next one, let's do 2/3 log of a half 6x cubed minus 4x. Okay, try those two. Okay, so when we take the derivative, the 7's going to stay in front. Then how do we take the derivative of the log 7 of x? It's going to be 1 over whatever you're taking the log of, which is x. But to deal with that 7, it's the ln of 7. Then the derivative of 1x is 1. So that is going to simplify to 7 times 1 is 7 over x ln of 7. Now, quick question. 7 over 7, does that simplify to 1? 7 over 7, does that simplify to 1? No, 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 no. This is not 7. This is what? ln of 7, which is a whole nother number. So those are the little mistakes people make. Be careful. Be careful. Not the same. Okay? You're like, you tricked me. I did. Okay? Now, when we take the derivative of the next one, again, being careful, the 2/3 in front stays in front. We're going to do 1 over whatever you're taking the log of original, 6x third minus 4x in parentheses. You'll notice that I keep putting parentheses because next to it, I'm going to do ln the base, which is ln of a half. So to keep those separate, the parentheses do matter. Times the derivative of that, which I'll put in parentheses as well, which would be what? 18x squared minus 4. So stop there. You may be worried about simplifying before you even get there. So step 1, make sure you did the derivative correctly. Then, when you know the derivative is correct, then we will simplify. 2 times 1 is 2, and then I'll just keep this in parentheses, and it'll go nice and slowly. On the bottom, we have 3 times 6x cubed minus 4x ln of 1/2. Now again, you can totally leave it like that. No problem. Or if you want to distribute the 2, you get 36x squared minus 8 over, in parentheses, 18x cubed minus 12x, in parentheses, ln of a half. Okay? Either one is fine. Either one is correct. And now we'll do the last special case. So all of these kind of stick out like a sore thumb. E, obvious. ln, obvious. Log, obvious. This one's a little less obvious, but it's still a special case nonetheless. And the reason why it's a special case is an example of a base, any number, a base, any number raised to a variable. That one is weird. It's not 3x. It's not x to the third. It's a number raised to a variable. It's a number raised to the variable. So that is also a special case. Any number, any base, fraction, decimal, negative, whatever, raised to a variable, whatever the variable is, that's a special case as well. And here are the steps to take the derivative. Step 1, probably your favorite step, rewrite it. Step 1, rewrite it. Now, that 3 is a base. And if you remember from log, how do you deal with bases? ln of whatever the base is. Not divided by it, but just ln of whatever the base is. And it kind of looks like we're done. I rewrote it. I took care of the base, but there's something I have not taken care of, and that's the exponent. The last step is the derivative of the exponent. What's the derivative of 1x? 1. and it doesn't change anything. That's why when you see when they explain it, they never show you the 1, but there's a 1 there because the process has 3 steps, not 2. The reason why they don't show you the 3rd step is because it's 1. Anything times 1 is, it doesn't change anything. But that's why I like to do the more complicated ones, because then you see the full process. So let's say we had a base like 6 raised to 8x to the 5th minus 7x squared. Okay? Let's say we had that. Well, I have to first identify that it's a special case. It is a special case. Why? It's a number raised to a variable. As soon as I identify that, now I know I have 3 steps to follow. And again, write the steps if you need it. Whatever's going to help you tomorrow to remember your page of notes, that's what you need to do. Okay? Step 1, rewrite it. Step 1, rewrite it. Step 1, rewrite it. Everybody likes step 1? Step 2, ln of whatever the base is. That's how we deal with bases. And then step 3, the last step, in parentheses, to be careful, derivative of the exponent. And the derivative of the exponent would be 40 x4 minus 14x. And to be honest, I'm just going to leave it like that. I'm not going to simplify, because how would you simplify it? You could distribute the ln of 6, then I have 2 of them. Why would I want that? I could turn it into a number, but it's going to be really ugly. It technically is simplified. I wouldn't mess with it at all. That would be it. Okay, so let me give you just a couple examples for this one, and we'll do a few word problems, and we'll stop. Let me just give you one example. Let's do 2 raised to the x minus 8 x squared minus 4x plus 3. And then of the other special cases, ln, log, or e, which one do you find the hardest? E, ln, or log? Which one's the hardest ones for you so far? ln? Are you just saying that because you want an easier one? Minus, you're like, I know what he's going to do. 6 ln of, let's say, x4 minus 2/3 x. Okay, so I threw in another one. Through each one, nice and slowly. The derivative of 2 raised to the x, step 1, rewrite it. Step 2, ln of the base. Step 3, derivative of the exponent. The derivative of 1x is 1. That's why you'll see they just teach you this one, and they don't put the 1, but they're not really showing you the full process. Okay? Then the next one, write it in order. Step 1, rewrite it. 8x squared minus 4x plus 3. Step 2, ln of the base. Step 3, derivative of the exponent, which is 2x minus 4. Okay, let's just pause there for a second. This would clean up, I'll put it here. This would clean up to 2 raised to the x, ln of 2 times 2 would just be 2 raised to the x, ln of 2. And then this one, again, I'd probably just leave it the way it is. There's really not much I see that would make it simpler or make my life easier. It would just be the way it is. Okay, now the reason why I did that is I want to make myself a little space here. I'll try to squeeze it in. Let's look at that. So the minus 6 stays in front. How do we do the ln? Take the derivative. We go back to our notes. It's 1 over whatever you take the ln of, x to the 4 minus 2/3 x. There is no base, so we don't have to worry about that. So it's times the derivative. The derivative of x to the 4 is 4x third, and the derivative of minus 2/3 x is minus 2/3. So let me rewrite that over here. So we have minus 6 times 1, which doesn't change anything, times 4x to the third minus 2/3 over x to the 4 minus 2/3 x. Sorry, that's so small. Make it a little bit bigger for you. Okay. Now, yes, you can leave it like that, or we can distribute it, right? We do have to figure out what we're going to do with that minus. If we leave the minus, then it's a minus. We don't have to worry about the minus anymore. Okay. Then if I distribute the 6, that would be 24x to the third minus 12 over 3, which is 4, over x to the 4 minus 2/3 x. Now, as you're looking at that, are you worried about the algebra cleanup at the end? Or are you worried about the derivative in the beginning? That's going to be the big question. And hopefully neither. So how do we do word problems, or how does this fit in? Well, we're going to do the first one together, not stress about it. And the second one will be a little bit more involved. So this one says an online store sells guitar strings. If the store sells X sets of guitar strings at a certain price per set, then the price demand equation is this. So let's be clear. P stands for price. 12.5 times 0.998 raised to the X. X is how many sets of guitar strings. When you buy a set of guitar strings, you get all 6 strings. Okay, so that's what a set means. So are we okay with the original? Okay, now the question is, if I get 100 sets, what would this be? Okay, 12.5 parenthesis 0.998 raised to the 10. Go to your calculator, put this in Y1, be careful, put that in Y1, go to the table and get that answer. Okay, so put that in your calculator, Y1, go to the table, plug in 100, plug in 100 and see what you get. So I'm going to go to my calculator, go to Y equals, in Y1, I'm going to put the equation 12.5 parenthesis 0.998 close parenthesis raised to the X. Then, as we learned over and over again in the other chapters, you go to the table, plug in 100, and you get 1023. 1023. But again, everything has to have meaning. Wait a minute. 100 sets of guitar strings cost 1023? Does that make sense? Why not? What does it say? Per set. So this is each. This is each. So hopefully that makes a little bit more sense. I'm not going to write the sentence, but 100 sets of guitar strings would be 1023 each. Good so far? Now, the question is, I want to know how that is changing. As soon as I say the word changing, that means we're going to do what? Derivatives. So what I would like you to do, just going to give you a minute, take the derivative of this. Take the derivative of this. So looking at this one, all right, it's definitely unusual. Is there an E in there? Nope. Is there an ln in there? Nope. Is there a log in there? No. It's the one where a number raised to a base. But what the heck is this 12.5? Well, let me remind you, on the previous examples, what was the 2/3? What did we do with the 2/3 that was in front? We left it. What did we do with the 7 that was in front? We left it. What did we do with the 4 in front? We left it. So when there's a number in front, what have we been doing with it? Leaving in the front. Now the reason is product rule, which we'll learn later, but bottom line, the 12.5 goes in the front. And then, I know it looks weird, but we have a base raised to an X. Step 1, rewrite it. 0.998 raised to the X. Step 2, ln of the base, 0.998. Step 3, what's the derivative of 1x? 1, so that really doesn't change anything. So you get the derivative 12.5 times 0.998 raised to the x times ln of 0.998. So I know that looks weird. I get it, but it's the same as before. What threw you off was the decimal, maybe. What threw you off was the number in front. But hopefully with experience, now we got it. And what I'd like you to do is put this in y2, use the derivative in y3 in the calculator, and see what you get for the derivative at 100. See what you get for the derivative at 100. So you're going to go to y2, put in your derivative, y3, derivative in the calculator, then plug in 100, and not only can we get the answer, but we can check the answer as well. So we found the derivative. We go to the calculator. We go to y equals. I'm going to put my derivative in y2, which was 12.5. Parentheses, you can do without parentheses, 0.998 raised to the x times ln of 0.998. And again, if you're like, I'm a little worried, what if it's wrong? We're checking the calculator. Math under y3, 8. Again, depending on your calculator, x, vars, y vars, 1 for function, y1, x. If you have the other form of the calculator, it's math 8, y1, comma, x, comma, x. But when I plug in 10, second graph, -2 cents, -2 cents. So you should get -2 cents. And the question is, what is that? Well, what's happening is at 100 sets of guitar strings, price, how is it changing? Decreasing 2 cents. So the price of the next one should be 2 cents less. The price of the next one should be 2 cents less, which is 10.21, right? That's how the price is changing. Right now it's 10.23. What am I expecting that price to do? It's going to decrease 2 cents. It's going to decrease 2 cents. So let's put that per set. Perfect, perfect, perfect. All right. Last word problem. This goes back to what I showed you in 3.1. Continuous compound interest rate. That formula is A equals, A stands for how much is going to be in your account, equals P, which is principal, times E, the symbol E, raised to the R, rate, to the T, time. And this one, I'm just going to help you out a little bit, says you decide to invest $10,000 at a rate of 4%, 0.04 T. That is your equation. And we want to know, how much will I have in the account after 2 years? Take the derivative and find out how much is the account changing in 2 years. Okay? Give that one a try. So I'm going to put the new problem in my calculator. So I'm going to go to my calculator, go to y equals, get rid of y1, I'll get rid of y2. I can leave y3 in there. And then y1 will be 10,000. Be careful how you type it in. We spent a lot of time on that. Second ln for E raised to the 0.04x. Make sure that all of it's raised, either in parentheses or like that. Make sure it's 0.04, not 0.4. Be careful of those little things. Then when you go to the table, plug in 2, everything has to make sense. What does 2 stand for? 2 years. What's the 10,833? That's how much is in the account, right? So again, everything has a meaning. So we get $10,833. I'm not going to write the sentence, but after 2 years, that's how much you have in your account. It's pretty good. You made $833 just like that. Okay. And to take the derivative, we go to our sheet, we look it up. The 10,000 stays in front. How do you take a derivative of an E? Step 1, rewrite it. Step 2, derivative of the exponent, which is 0.04. Stop there. Yes, that is a complete answer. But the point of simplifying is this can be rewritten a little bit easier. And I can take the 10,000 times the 0.4, and what will that be? 400 e to the 0.04t. That is a lot easier than to have to put 10,000 times the e times the 0.04, right? That's why we simplify. And we can check that by going to the calculator. Oops, calculator. Go to y equals, and we put in 400 e to the 0.04x. Y3 is the derivative in the calculator. That's a good way to check our work and see if we didn't make any little mistakes. And notice both of them is 433.31. 433.31. So writing this in a sentence, 31, right? Type it so you have a better chance of being able to read it. Okay. At year 2, the account is what? Increasing $433.31 per year. Okay. Now, again, to really bring this home, you're stopping and looking at your account. You have $10,833. What is this number telling you? How much more next year? That's an estimate for how much more, how it's increasing per year. Okay. And that is a good place to stop.